In the first video on integration by partial fractions, we studied rational functions, polynomial divided by a polynomial, where the polynomial on the bottom could be written as a product of non-repeating linear terms. And when we had this, then what we would try to do is a little bit of algebra where we would manipulate it so that it was a constant divided by each of the different linear terms in turn. And then we would go and do some algebra to try to figure out what the a, the b, the c, and so on were going to be. But in this video, we want to talk about, well, what happens if it repeats? And what happens if there's a term that is non-linear? For example, consider this quadratic term. Imagine this was in the denominator, something like x squared plus 1. And the question is, can we factor that as a product of two linear terms? Well, if we could, then the a and the b here would be 0. So I'm interested in studying what are the zeros of a quadratic like this. However, there are no real zeros of this. Indeed, if you move the 1 to the other side, then you're asking, I want to square a number and have that be negative. It's just not possible. Or alternatively, I take a square root of both sides. You're asking, what is the square root of minus 1? It is not a real number. So as a result of this, we're going to say that x squared plus 1 quadratic, this is something we call irreducible. And what that means is it has no roots, no zeros that are real numbers. There's something called complex numbers, and it will have solutions over there, but that's a topic beyond the domain of calculus 2. But nonetheless, I'm not able to factor it as the product of two linear terms with real numbers. And more generally than that, if I take a generic quadratic, an ax squared plus a bx plus c, then we know how to factor this by the quadratic formula. The formula is that x is minus b plus or minus the square root of b squared minus 4ac all over 2a. It's a mouthful. But the point is that this is only doable. I can only use the quadratic formula if the thing inside of the square root is positive. So I can only find two factors, and therefore will only be able to factor it as a product of linear terms if we have that b squared minus 4ac being positive. So when that's not the case, when it's negative, we call it irreducible. There's nothing we can do to these quadratics. They just sit there and I cannot break them up as the product of linear terms. Okay, so now I'm trying to do partial fractions. I've got one of these quadratic factors on the base. What can I do? So if I have an irreducible factor, some quadratic that I cannot reduce into linear terms, then the thing I guess in my partial fraction decomposition is you put the quadratic on the bottom, but now you put a generic linear on the top, not a generic constant. So that is, I guess, an ax plus b, and I have to find both the a and the b. So as an example, in this one I have one linear and one quadratic on the bottom, and what I'm trying to do is do a partial fraction decomposition. For the linear term, the x minus 1, I just put a constant. It's a over x minus 1, and that's what I'm going to guess. But for the quadratic term, the x squared plus 1, I put a generic bx plus c. That is a generic linear term up in the numerator. So that's how I deal with quadratics. But what happens if things repeat? Well, in that case, there's another little bit of a trick that I need to do. So if I have a repeated factor, that is the same linear factor but multiple times over, then what I have to do is guess all powers of it. What I mean by that is if I have something like a over x minus 1 squared, I want to guess a term that's got x minus 1 in the denominator and a term that's got x minus 1 squared in the denominator. And for both of those, I put a constant a and b up on the top. If this was higher, say x minus 1 to the power of 5 on the bottom, you need an x minus 1 and x minus 1 squared all the way up to an x minus 1 to the power of 5 with an a, b, c, d, and e constants. It can get a little bit complicated, but the basic idea is if you have a repetition, you use the highest power and all of the lower powers. Those are the terms you need to add. Okay, let's test it out in a concrete example. So in this next example, let's analyze what goes on in the denominator. I have a couple things. First of all, I have a linear term that is repeated. When I look at the yellow x squared there, this is a reducible quadratic, not an irreducible one. X squared can be written as x minus 0 times x minus 0, just x times x. So this is a repeated linear factor, not an irreducible quadratic. But x squared plus 1, as we saw before, is an irreducible quadratic. So what is the guess for my partial fraction decomposition? Well, it's going to have 4 different constants. For the repeated linear, the x squared, I put an x squared term and an x term. So an a over x and a b over x squared. And then for the irreducible quadratic, I have to add a linear term up top. So I put the irreducible quadratic in the bottom and then a cx plus d up on the top. So this is my decomposition, but now I have to try to figure out what is the a, b, c, and d. So that's just going to take a little bit of algebra. It's very similar to the first example, but we've got more constants and there's more tricky things, and the integrals at the end get a little bit trickier. So let's see how that works out. Well, the first thing we're going to do is we're going to multiply everything by the denominator. Really what I think about is multiplying by the entire denominator and then canceling whatever appears. So for example, for the a over x, I remove one factor of x, and therefore I get multiplied by the other factor of x and the irreducible. Now I'm really getting squished down here, but I'm going to write it all out. So I've got my a, b, c, and d, and all of those are multiplied just by polynomials. I remove myself entirely. Now what I want to do is a bit of a rearrangement. Instead of having it a, b, c, d times various things, I want it to be powers of x times the various constants. That is, if I rearrange this, I can say that in front of the x cubed terms, there was 1a and 1c. In front of the x squared terms, there was a b and a d. In front of the x term, there was an a. And in front of the constant term, which I'll write down as a 1, there was just going to be a b. And then on the left-hand side, I've done nothing more than just color code the polynomials. And I will note that there is, in fact, a x cubed term here. It's just 0 times x cubed. And there's a constant 1 term here. It's the 3 times the 1. So even though I only have x squared and x highlighted in blue, all 4 do appear on the left-hand side, just implicitly. All right, hello again. This equation that I have here is actually 4 different equations. They vary independently depending on the powers of x. So there's a cubic term, a quadratic term, a linear term, and a constant term, and I can pull them out of here. So for example, the cubic term, well, there's no cubics on the left-hand side, so just 0. And then on the right-hand side, the cubics are a plus c. For the quadratic term, there's a 5 on the left-hand side in front of the x squared, and on the right-hand side, a b plus d. So I set 5 equal to b plus d, and so on. So the big 1 equation in terms of the x's has separated into 4 different equations. How do I solve this? Well, the final 2, it turns out, are really easy. So a is 1 and b is equal to 3. Good, I don't have to do any work. But now that I know that a is equal to 1, let's look at what happens from the top line. If a is 1 and a plus c is 0, then that's going to tell me that c is minus 1. And likewise, if b is 3 and 5 is b plus d, so 3 plus d, then that means that d has to be 2. So now I have my a, b, c, d, and what I want to do is I want to take these and put them back into that partial fraction decomposition. Well, I've got my numbers, so let me go and move them in. And now I finally have something that's nice, something that I can go and try to integrate. Remember, we began with a messy rational function that we didn't know how to integrate. We have now done the algebra of the partial fraction decomposition and turned it into something that hopefully, we'll see in a moment, that hopefully is going to be a little bit easier for us to integrate. Well, how should we do this? What I'm going to do is, first of all, wrap everything in terms of an integral sign. And the first 2 integrals are pretty easy. Their very first one is just going to be a logarithm. 1 over x goes to logarithm. The second is just a power rule. This is 3x to the minus 2. So it goes to minus 3x to the minus 1. Now, the third integral, however, is a little bit more complicated. You notice right off the bat that the sort of obvious u substitution of the denominator, it doesn't work out. The du is not the numerator. So one thing I can do is try splitting it up as 2 different integrals. So I'm going to do that. I get a minus x on the top over this thing on the bottom, and I get a 2 over this thing on the bottom as 2 separate integrals. Maybe that's going to make my life easier. Well, in this particular scenario, now a u substitution does work. In other words, if I set my u to be my denominator, so an x squared plus 1, is du is a 2x dx, I have an x on the top. So outside of the factor of 2, which I can divide that, I get a minus 1/2. This just looks like 1 over u du. And I know how to integrate 1 over u. That's just going to be a logarithm. So I can replace this with negative 1/2, the logarithm of u, and u is x squared plus 1, so the logarithm of x squared plus 1. And then finally, I have to go and deal with this final 4th integral, and this one is either jumps out at you or it doesn't. This is the antiderivative of arctangent, or more precisely, twice arctangent. So I put that down, I add my plus c, and I am done.